So welcome to the final academic seminar of the semester. Please turn on your cameras and ask or upvote questions in the Slido. This is the last event of the PEP package, so be sure to fill out the final feedback form. A reminder that SUCE subcommittee applications will close next Friday, so definitely check those out if you'd like to join the team. I'm excited to welcome Dr. Kapil Chauhan, who will give a presentation on the dispersion in the urban environment. I'll hand it over to him now. Please make sure to turn your cameras to welcome him.
Thanks, Sangeeta. Good evening, everyone. I'm glad that this event has been going on for a while, and I think this is an excellent platform for students to learn more about what's happening in the labs, particularly. I'm an experimentalist, so I'm always happy to talk about experiments, which I will do today. Before we start, I want to just make sure that I want to acknowledge and pay respect to the traditional owners of the land on which University of Sydney stands, which is the land of the Gadigal people of the Eora Nation. I'm currently in the beautiful land called Bulanaming, which is commonly known as Marrickville. Something about me, I did my undergraduate degree in mechanical engineering, although I work in civil engineering, which will something that you will appreciate later on, that fluid mechanics is common to many of the disciplines. So it is used in mechanical engineering, civil engineering, chemical engineering, biomedical, and so on. So you don't have to be confined to your undergraduate degree. That's the message here. So I started as a mechanical engineer, and then I did my master's and PhD degree in US, where I did computational fluid dynamics and then a theoretical PhD on turbulent boundary layers. I moved to Australia to work at University of Melbourne as a postdoc researcher, and there I started expanding my area of interest and did many other things. But then, given my background in experimental research, I found a position at Sydney, and I've been at Sydney since 2015, and now I'm a senior lecturer. Here, I've been involved with the boundary layer wind tunnel, which is a big facility, multi-million-dollar setup that is used for wind engineering applications, but also to study turbulent boundary layers. I'm also in charge of few courses in the department. So many of you know me from fluid mechanics. That's the biggest course I teach. If you're in the first and the second year, you will be seeing me soon. I also teach some electives, which is 5999 and 5670. If you have any questions about any of those, you can message me. So we are going to talk about dispersion. So let me show you an example of dispersion in the urban environment. And this is a video from the bushfire that was in 2013. And since then, we have had many bushfires, but this is a very good example of what can happen due to dispersion. Okay. So here you can see that the bushfire was in the Blue Mountain region, which is many or at least 100 kilometers away from Sydney CBD, and the smoke is traveling all the way towards the coast. And you can see very interesting characteristics here. When the movie starts, the smoke is kind of uniformly mixed, but later on, as the day develops, you can see that the smoke is only confined to the upper regions of the atmosphere. So there can be a case where the smoke is brought towards the ground and reduce the air quality, but there can be a case where the smoke is confined to the upper regions and the air quality is not that bad near the surface. Okay? And these things play a role in what is important when we look at dispersion. More importantly, the flow and the surface characteristic. So by definition, we want to say dispersion is the process of distributing something, where the phenomena itself is when a scalar, okay, a quantity which is only in magnitude, is spread by the action of fluid motion. Okay. Very generically, we can say we are dispersing a crowd, and that means that it's just spreading out. Okay. If you leave a very packed football stadium, the crowd is dispersing. Scientifically, we are talking about a scalar quantity where it is emerging from a known or a fixed position, and then it's going somewhere else by the action of fluid motion. Scalars in the urban environment then can be classified or categorized in different groups. And this could be pollutants in air, which usually come out from factories, automobile exhaust. They can be toxic. They can be accidental chemical leaks. There could be scalars or contaminants which are dispersed in water. And this could be in rivers or brine discharge in ocean. And then scalar is also temperature. So you can have temperature as a scalar quantity mixing with the environment because of urban heat islands. And then there is also odor, which is smell. Scalars can be passive. When they are passive, they follow the flow and they cannot influence the flow field. So in this example here, what you see is that some smoke is released from these tubes and it just follows the flow and it gives you an instantaneous idea of where the flow is going. And it can be active. So this is something that you would see in a volcanic eruption or where the smoke is hot and it will rise up by itself. So there is no external forcing needed for it to go along its path. An important aspect of scalar dispersion is also the geometry of release. So there is a point source. So point source where the location from which the scalar is emerging is quite small or a point-like compared to the domain in which it is dispersing. Okay. It can be a line source. So think of a traffic jam and all these cars are exhausting some toxic chemicals and then it's coming out in terms of or looking like a line source. And then there are area sources. So bushfires or smoke coming from bushfires are large area source. Open landfills, they release odor and they are also an area source. Other complexities could be when these scalars or these contaminants are chemically reactive. When that happens, they induce highly non-uniform source. Okay, so it's like a volume source and it's not uniform. So sometimes you have a very strong chemical reaction happening in some part of the plume or the flow, whereas in other part, it might not be that strong. Okay. You also need a priori knowledge of the chemical composition, which is changing at all the time. And there is a significant variation in density. Okay. You can have particulate matter, which is quite commonly known as soot, or you can think of the terms PM 2.5 or PM 10, where the matter is 2.5 microns diameter or smaller, and PM 10 is 10 micron diameter or smaller. Okay, and because they are solid, okay, they're solid particles, they have higher density than surrounding air, and they don't strictly follow the flow because they have a settling velocity. And it depends on how strong is the forcing wind. If the wind is strong, then they almost follow the flow, but otherwise they will deposit somewhere else. Okay. Why are we studying dispersion? It's an important problem. We know that because everything that we know about air pollution is not good. Okay. There are some interesting numbers to look at. So I didn't think of this when I started this research, but more people on our planet live in urban areas than in rural areas. Okay, and as of 2021, there are 35 megacities, which means that there are more than 10 million people in each of those. So a substantial population of our planet is quite congested, quite living in crowded environment. And in all these environments, all the activities that we do, which taking transportation, infrastructure requires energy, and we have emissions coming from those activities. Okay? These emissions usually lead to air pollution, and they cause a lot of health problems such as asthma, cardiovascular disease, and so on. Okay? Particularly, particulate matter is significantly harmful, which is why there is a significant push to get rid of diesel exhaust and cars which have conventional combustion chambers, okay, which is why electric cars are preferred now, okay. But unless we generate that electricity using a clean source, we are not solving the problem, we are just pushing it somewhere else. Okay. Again, there is a health issue associated with air pollution. So these are the numbers from a study that was done in 2013. I don't have the latest numbers, but the significance is evident here, where the number of deaths occurring due to air pollution itself is more than anything that we have seen. I think these numbers are even worse than COVID. Okay. So, and there is a significant jump in 5 years. Okay. So you can imagine that if we keep increasing the urban density, these issues will become more and more severe. Okay. So what do we want from studying urban dispersion? Okay. So the expectation is that we cannot get rid of emissions, at least not until 2050 when we want to go to net zero. Okay. So emissions are part of life. Okay. And they could be sustained release from known sources. So this is a chimney stack where the smoke from the M4 tunnel is collected by those big fans that you might see in tunnels, and that they are released through this chimney stack. Okay? So this is something that we know, and how do we address this long-term release? This is going to keep releasing exhaust over many, many years. Okay? So how do we predict what's going to happen to the regions around it and where the smoke is going? There could be also accidental release, okay, and this is temporary. This could happen over a period of hours or few days or weeks in terms of bushfire, and then we want to predict where is this going and what would be the impact in the surrounding. So practically, we want to estimate probability of accidents. Okay, so if you look at this flow and you just say that, okay, there is 0 concentration of smoke here, but 100% smoke here, so then we can characterize the concentration, okay, by a number. Okay, and we want to calculate the probability of accidents. So what are the chances that local concentration of contaminant, so contaminant is a generic word, okay, that will exceed a threshold or a dangerous level, because it can lead to issues like asthma, or if it is a flammable or toxic gas, then it can lead to combustion. Okay, which locations in space are more likely to be at risk? So again, going back to this, if this plume is always going up, then only the regions around it will be affected. But what happens is, due to the atmospheric turbulence, it is very likely that the smoke is going to come down again. Okay, and we'll talk about that a bit later. And then it can create issues for people who are not in the vicinity of the source, but many kilometers away. Okay? And this probability of accidents we need to know for emergency response. So what action needs to be taken? Exposure time is something that is used for urban planning and policy. So for long-term exposure, we want to see, okay, if you have, let's say, a sewage treatment plant, okay, and there is some odor coming out of it, okay, and it's going to be there for many, many years. So then the development will prefer that there are no residential areas around there. because their quality of life will be affected by that. Okay, so you want to predict what would be the impact of a sewage treatment plant in the surrounding neighborhood. You want to predict what would be the impact of a chimney exhaust, okay, out of M4 to the surrounding neighborhood, how long it will be, or how tall it would be. And these things can be understood by looking at exposure times. Okay? And this could be intermittent, but they can be modeled. So ideally, we would like to have the capability of predicting urban dispersion in a scenario like this, because physical sensors, they are limited. I cannot have a physical sensor placed at every corner of Sydney CBD. Okay? There would be just too many and too much data to keep track of. Okay? So what we would like to do is simulation. Okay? So this is a simulation of an accidental release where something has given up here and then it is moving due to action of wind and it's spreading in the CBD area. Okay. To do this, we want to do simulations using the governing equations. So there are two governing equations that we need to keep track of, the flow itself and the concentration. Okay. Fluid flow is governed by a set of nonlinear partial differential equations known as the Navier-Stokes equations. I don't have this slide to scare you. I just have this slide for you to appreciate that things get complex very easily. Okay. This I show in my course too, and I don't expect students to remember this equation, but they are there. You can't get rid of them. Okay. So we know that dispersion happens by fluid flow. So if you want to know the fluid flow, we need to solve these equations. So we need to solve these three components of velocity and pressure using this set of equations. Easier said than done, because Navier-Stokes equations, they don't have a solution. Okay, there is an institute called Clay Mathematics Institute that has outlined 7 problems, and if you solve one of those, which is a Navier-Stokes equation or anyone else, you get a $1 million prize. Okay, Navier-Stokes equations are still not solved. Okay, which is a big problem. These were formulated in I think it was the 19th century, early 19th century, and it's more than 150 years, and we still don't have an analytical expression for these. Okay, so we have a phenomena which is governed by a flow which has equations that cannot be solved. Okay, on top of that, we have the scalar dispersion equation. Okay, where there is a source term, there is a diffusion term, and there is an advection term, and this is the time variation, which is often ignored for steady state. But advection, this is the term which is governing how a scalar quantity phi will move in the flow. Okay, and this requires knowledge of velocity. If we don't have knowledge of velocity, if we can't solve the Navier-Stokes equation, we can't solve the dispersion equation. Okay, so we are limited by those factors. So ideally, we would like a solution which is saying that, okay, what is the concentration at a given location, given wind speeds, a given pressure, temperature, and time. Okay, but that is not always possible. So these equations we cannot solve, and there is an additional complexity where flow is also turbulent. So here is an example of flow visualization where some smoke is released in the atmosphere. So these are field experiments, and you can see that it's not moving smoothly. Okay, there is some fluctuating behavior, and this fluctuating behavior keeps changing. Okay, it's not that it is just moving randomly. It keeps changing direction. It's very erratic. Okay, this is a turbulent flow. Okay, turbulent flow on top of Navier-Stokes equation that cannot be solved create more complexity. Okay. So we are left with solving these equations by numerical methods. Okay? Something like Newton-Raphson or RK4 or something like that, we can use and do a numerical simulation. Okay? Numerical simulations are challenging because the flow is turbulent, okay? And it requires us to resolve things at many different scales. So if you look at the plume here, okay, at the source, it is only this big. Okay, it has some diameter which could be a few hundred meters. Once it goes up in the atmosphere, its diameter could be of the order of kilometers. And then it has these big bulges, then it has small scale features. To resolve this, we need fine mesh to do the computations. Okay, so if I take a grid which is only this big, I can only know features which are this big. Okay, I cannot know the details that are residing in this box. If I take a grid which is smaller than that, then the details I get are bounded by the size of the box. And if I want to know the finest features, then I have to make my meshing even smaller. Okay, so this is similar to having more pixels in an image. If you take a photograph and if the photograph is at high resolution, you see more details. Same goes with doing numerical simulations of fluid flow. If you have more points in your domain, then you get better details of the flow. You want more details, but then it comes with the cost of computation. Okay. So if you look at this example here, okay, let's think of a box where we take a box which is starting from the source, going all the way up to the Sydney CBD, and that is about 100 kilometers long. We will take the box to be 20 kilometers wide, and in the vertical direction, we will take 1 kilometer. Sorry, this should be 1 kilometer, not 1 meter. Okay, so we are hoping to simulate something which is 100 kilometers by 220 kilometers by 1 kilometer. And the desired resolution is 10 meters. So at every 10 meters, we would have 1 point, resulting into 10,000 by 2,000 times 100 grid points. Okay. And then we have to represent these points for velocities, pressure, their derivatives. So the memory requirements just to represent the primary variables at one time step is 600 GB. This is an estimate. Okay. If we are going to do unsteady simulation where we want to do prediction of dispersion at many time steps, then the memory requirements is even higher. Okay, and calculations on this big large matrices and taking derivatives is quite slow. Okay, so we have to be smart about the simulations itself. Okay, so in practice, what we do is we do something called a Reynolds decomposition. Okay, and the equations are not of importance here. What is important is to understand that the actual fluid flow, the velocity will depend on where you're looking at. So it depends on X, Y, and Z, which is the space and time. So we represent that velocity by a mean component, which is not dependent on time, and a fluctuating component, which is dependent on time. When we do that, we can do the same thing for concentration. And we can decompose our flow into a mean component, which is not dependent on time. And the time dependent component is called the fluctuating part, and we model it. So we don't calculate that, we just approximate it by some empirical relations. Okay. And when we do that, our equation for the scalar, so now I'm using C as concentration, we'll have the advection term, but now the advection term is for the mean quantity itself. Okay. And there is no time dependent term here. And then it would have diffusion, which is based on the flow properties. Okay. Diffusion of scalar depends on the scalar itself. And then we have this terms which are due to turbulent transport. So these are the terms which are responsible for mixing the scalar in a random and erratic manner. And these terms are something that we approximate. Okay. So we don't calculate them, but we use empirical relations or functional forms to approximate them. Okay. These are not known beforehand, so we have to estimate them based on measurements or some kind of theoretical arguments. But because they are approximations, they also induce some error. And in practice, if we get our concentration prediction within 50% right, we are doing a good job. Okay. That's being changed because we have faster computers and people are doing very large scale simulations. But even now, for regulatory models, anything under 50% is acceptable. So one of the ways to simplify this equation, where we can calculate this left-hand side, we can calculate the diffusion term, but we cannot calculate this, is to replace this flux term by a gradient diffusion model by estimating an eddy diffusivity. Okay. And when we do that, we can then solve this equation and we can get an analytical expression for the concentration. Okay. And the analytical expression for concentration gives you a profile of the concentration in XYZ such that in the X, it is moving with the wind direction, and in Y and Z, it is spreading according to a Gaussian profile. Okay. So this is called a Gaussian plume. Okay. The trick here is to prescribe this half fits. So it will spread in the Y direction or the lateral direction. It will spread in the vertical direction. And we have to prescribe those growth rates based on experience, experimental evidence, and that will change depending on the local conditions. Okay. When we do that, we can very well estimate what with the concentration and associated. There are empirical models which will also give the probabilities. Okay. So this is what's been done in most engineering consulting, where if you want to do a study for regulatory purposes, you will utilize a Gaussian plume model to predict what will happen to the concentration. Okay. In Australia, we use packages, so you don't have to do this by hand. There are packages available in Australia. The most common ones that are mandated by the local environmental agencies would be air mode, CalPUF, or OSPlume. Okay, there are many local models available worldwide. Now these are local models because this spread, these quantities that we prescribe will change depending on where you are. Okay, so if you prescribe this in a flat area, it won't be the same in semi-residential areas. Okay, so different authorities or different local regions will say, okay, use this model because it works better for our cases. Okay. In urban areas, something like Sydney CBD or Melbourne CBD, we cannot use the Gaussian plume model. Okay. This is because interference by the building and structures disrupt the scalar transport. Okay. Flow structures are dominated by the local landscape. Okay. So let's look at this animation again. And you see this dispersion coming behind this tall building. And then the final outcome has nothing in common with a Gaussian profile. Okay. There is no resemblance to a Gaussian plume. It has gone in random directions because of these obstructions. There is a big obstruction here. There are small buildings around here. Okay. And there would be regions where there would be recirculation and stagnation. So obviously we cannot apply Gaussian plume model here. If the plume was released somewhere in this region where it's relatively flat and there is no disturbances in the flow, then we can probably apply the Gaussian plume model, but not in the urban areas. Okay? And this is why urban flow is quite complex. not just for the flow itself, but also for dispersion. Urban flow is characterized by a canopy layer where the flow is dominated by the presence of buildings and trees and other landscape structures. Okay. And in this region, you will get a lot of backflow and recirculation, a lot of regions where there would be stagnation of flow and the concentration can get trapped. On top of that, there is a roughness sublayer where there would be turbulent motions which are induced by this building. So you have a flow coming from the atmosphere, which is the atmospheric boundary layer. The winds are coming and they will interact with the structure and there would be shedding. So you all know about shedding. Behind, there's a very famous example of the Tacoma Bridge. And then you would have thought of shedding in that context. But basically what happens is that the flow comes here and then it will start swirling behind those buildings. So in this region, there is a lot of swirling happening. Then there is an inertial region where these motions are almost of the same size such that there is a constant flux. So when we say constant flux, it means that the momentum exchange between the top and the bottom is constant. And then there is an outer region where there are large scale motions, and these are substantial, where you would see velocities of the order of 40, 50 kilometer, 40, 50 meters per second. Okay. Urban flows are complex, not just because of the presence of the urban environment, but also because of the surface. Okay. Because in the urban environment, you will get some distribution of velocity going from very high at the top and low at the bottom. But in a area like Sydney or Melbourne, which are coastal areas, okay, you will have flow which will suddenly change from a very dense roughness area to a smooth or relatively smooth region over an ocean. Okay, and in that case, the profile or the change of the velocity from the bottom to the top changes quite significantly. So the incoming flow will also change. So if you have a plume emerging from this region, it will spread differently under this profile compared to plume emerging from this region, and it will spread differently in this profile. Okay, so when you have mixed surface characteristic, that will also lead to complex considerations. Okay, so in Australia, we have terrain categories to categorize this. Usually anything in the urban region would be in terrain category 3, which means that there will be a strong presence of turbulence in the flow. At the same time, in the urban region, you also have effects coming from stability. So stability is something which is where you have a daily cycle of day and night, where the surface gets heated during the day and it cools during the night. Okay. So the temperature of the atmosphere going from the bottom to top will be different depending on the time of the day. So when you have an unstable layer, the surface at the bottom is quite warm, whereas the temperature decreases and it goes cooler and cooler further in the atmosphere. This is called an unstable layer because temperature at the bottom is lower, temperature at the bottom is higher, so the density is lower, and because of buoyancy, the flow will automatically wants to go up. So it's naturally unstable. And in those cases, if there is a plume, then it will meander very strongly. Okay? An opposite case would be a stable case where the temperature at the bottom is low, density is high, so it will try to remain in that configuration, and a plume will just not mix thoroughly, and it will just keep moving along the flow. Okay, and then there would be cases where you would have inversions. So there is a stable behavior, then there is an unstable behavior, and depending on what time of the day it is, the spread can be different. Okay, so we have to account for different flows, we have to account for different geometries, and we also have to account for different temperature conditions. And finally, in the urban region, you have something called urban heat islands. And these heat islands are something that have been extensively studied in the past few decades because of the secondary flows that they induce. So what happens in urban heat islands is that you will have regions where there is lack of vegetation and the coverage is primarily due to asphalt or concrete. And these structures or these surfaces absorb a lot of heat during the day. Okay, and they don't reflect anything back. And this heat is then stored during the day and then emitted back at night. Okay, whereas if you have a lot of green coverage, then the heat is absorbed, but then it is given back in form of transpiration or reflection. Okay, so what happens is that in these regions, you will see that there is a higher temperature of the surface, whereas in these regions, there would be a lower temperature of the surface. There is a temperature gradient. If you have a higher temperature and a low temperature, it will also cause something called a cross circulation. So flow will try to move from this region to this region. At the same time, you can also get thermal plumes where it will take the flow from the bottom to top because of buoyancy, and any atmospheric pollution in this region will be convected up in the upper atmosphere. So these things can happen too, and they are quite complex to model. Okay, so when we go back to our model where we want to model the fluxes, we have to take into account the change in the diffusivity estimates because of presence of cross circulation and thermal plumes. So what do we typically do in an urban environment? Okay, so we have these complexities. So what one does is that we cannot always model these things accurately. So we go to a very simplified calculation where we first do the flow calculation in this region. So depending on where you are, you would import the geometry of the region with appropriate resolution. So you can import the geometry of Sydney CBD, Melbourne CBD, or just part of it. And then you can say, I want to resolve the concentration at every 10 meters vertically, but every 500 meters in the horizontal and lateral, okay, depending on the details you want. Once you import that, you then solve atmospheric or weather forecasting model, okay, which will give you the flow. So this is a model which solves the Navier-Stokes equation, and it will give you what is the velocity in that box. Once you have the velocity, then you input that velocity to the transport equation for the concentration and use something called Lagrangian tracking at each time step to see where the concentration is moving. And then you will get the full picture where you have the flow and the concentration. The process, it requires many steps, and what we want to ideally do is do this in real time. So if there is an accidental release, we want to do this even faster than real time. So if the concentration is going to go from one region to another in, let's say, 30 minutes, we should be able to predict where it's going in less than 30 minutes so that we can do a better response. Okay, and this is where most of the research is aimed towards. Okay, the state of the art would be to do real-time prediction of dispersion in urban areas, but it is not that easy. Okay, so all the related research has been in these areas. So again, what I've shown you is a big picture. Okay, it requires lots of different researchers and research labs to work together, and then they're working on many different aspects of it. So climate models, or the ability to resolve the flow, is definitely one of them. There is always a component of numerical methods where we want to do faster computations, where we want to employ lattice-Boltzmann-like approaches, utilize hardware solutions like HPC and GPU computing. Machine learning and artificial intelligence is one of the things where people are trying to do novel things by something called Monte Carlo simulations, where instead of solving the equation at every position in the domain, you would try to do that in critical areas, okay? In areas where you would see the most gradients. Then, of course, there is something called subscript scale modeling. So when we do computations, and if I do a computation where everything is resolved at, let's say, 1 kilometer, what's happening in regions which are smaller than 1 kilometer? Okay, so those things have to be modeled. So that is called subscale modeling. Okay, mesh generation, this is not easy, because think of putting a mesh in a computational domain to cover the Sydney CBD. Okay, you will have to spend a lot of time in meshing that, making the model in any kind of computational aided design software. And then to discretize it is also a problem. Okay, people are doing full-scale experiments, and there are many full-scale experiments done where they just release some gas in actual field and measure it downstream. And then there is a component where people are doing scaled experiments in the laboratory and validation study. And these are the activities that we do in our department. So I think I have about 5-10 minutes. So I will quickly go through what we do in the School of Civil Engineering. So we have a boundary layer wind tunnel, which has a very large test section, and it's a amazing facility to do many different studies, not just dispersion. We do wind engineering studies, we do structures in there. Okay. And these are some of the characteristics. It has a big cross section, so we can put large models in there too. And there is a test section where we do all our measurements. Okay. And in this region, we can put roughness to create a boundary layer profile. So those profiles that I was showing, which were for different categories, you can generate in our internal. I hope this doesn't crash, because it did earlier. So let me go to the next one. So in this wind tunnel, we release smoke. So this is just a visualization. And this is a point source. Okay. And what you see is that, I think my computer will crash if I keep it running, but what you will see is that there is a meandering behavior. And although we are releasing smoke continuously, it breaks up very quickly, and then it starts coming in patches. Okay. So what's happening is that the plume, okay, so this plume is interacting with the background turbulence. There's turbulence in the flow, and that is the interaction that is governing where it's going. So what we want to do is we want to look at the influence of turbulence in spreading these things. Okay. So in our wind tunnel, what we end up doing is we release the tracer gas, we release it at some height and measure it at some distance downstream, and then we measure both concentration and velocity. So concentration is in blue and velocity is in red, and we get a Gaussian behavior, which is good. But then when we put building models, we don't get a Gaussian behavior because roughness interacts with it. And we do this at many different locations, and we repeat the experiments to cover a wide range of configurations. We did this experiments over many years, where we released at 8 different wall number positions to cover different turbulence levels. Okay, and there is sophisticated instrumentation required for this, where we have a photoionization detector to measure the concentration, and we have a velocity probe, which is a hot wire. And in reality, they look like this, and they're quite small. They are, so we want to measure concentration, so it is only 1 millimeter in diameter, and this wire here is also 1 millimeter. So we get very fine scale measurements in this flow. Okay, and that's what the time series looks like. So this is the velocity at a given position, and this is the concentration that is measured. And you can see that the concentration is not continuous. It's quite intermittent. And when it's intermittent, it is quiet for a time, there is no concentration, but then it spikes up, there is high concentration, and so on. Okay, and based on this, we can create a statistical picture of how the concentration is behaving. Okay, and we look at the probabilities of the concentration, and we find that the probability distribution function has an exponential behavior. Okay, and this exponential behavior is present at many different locations. So if I take the probability distribution function at all these positions, they have the same slope. Okay, and doesn't matter where I am. So we can see that there is some similarity. And we exploit this similarity and find that the slope of this exponential behavior does not change. Okay, whereas the coefficient, which is A here, has a behavior similar to the Gaussian profile. So once we have this behavior, we can then model this. We can model the probabilities of concentration based on these observations. And we have done the same thing for exposure time. So exposure time is where I want to see if the concentration goes beyond this level, how long does it last? And how long does it last if it goes beyond this level? Okay. And we have found that it has a power law behavior. Okay. And in this case, these are lines of constant probability, and they don't change at different levels. Okay. So we have done extensive studies to characterize the interaction of concentration and turbulence, and we have done studies to characterize the statistical behavior. Okay. And what we have done, which is novel, is documented the plume width across the whole flow domain, revealed the preferential orientation, and we have validated the exponential distribution, and we have discovered the log-log distribution for the exposure times. These things are, again, work in progress. I have 2 PhD students who are now looking at complex geometries and effects of buoyancy. So these plumes, or these experiments were done in the neutral environment. Now we're looking at a case where the gas that is released has a finite buoyancy such that it will either dip or rise. Okay. So final words from me is that dispersion is and will remain an active area of research because urban dispersion significantly affects the human quality of life, and accurate prediction is something that we want for both urban atmosphere and air quality. I will stop here so that I can answer questions and take more questions. But do let me know if you want to know details of something. I'm happy to have another one-on-one discussion with you on some of the things that might have interested you. But I found it challenging to put a big picture together, but not missing out on details either. So I hope there are questions. Thanks.
Thank you for that great presentation. I might screen share now the Slido questions that students have been putting in.
Yeah.
Okay. Can you see my screen? All right, so the first question was, why do inversions occur, as you showed in the graphs earlier?
Inversions occur because the simple reason is the rate of cooling does not happen. The cooling, so let's say everything is getting heated during the day, and surfaces like asphalt and concrete, they have a high latent heat than the air above. Okay, so at night time, the atmosphere few hundred meters away from the ground will cool faster than the surface. Okay, so because the surface is still giving up heat. Okay, and this is why you will get an inversion, that sometimes the rate of cooling is not same at all vertical positions in the atmosphere.
All right, yeah, that makes sense. So the next question was, how serious is a problem regarding smoke contamination on water quality in our dams?
So it is an issue where you will have air pollution, okay, or something like soot and ash from bushfires. It will get either washed from runoff, or because of rain, it will go into waterways and gets into reservoirs. If there are particles, then they will eventually settle, and they are routinely cleaned by something called dredging. However, it's not a substantial issue because most of the times there is a significant filtering happening later on. So smoke, I would say water quality has more challenges than contamination by smoke. Yeah.
Okay. So does climate change play a role in dispersion, and what is the future of eco-friendly cities?
Climate change does not play an immediate role in dispersion. So everything you see in dispersion is in the time scale of hours and days. Okay? So dispersion is something that's happening over time scale, which is quite small compared to the time scales of climate change. So for climate change to have dispersion or air pollution or contaminant in the atmosphere can contribute to climate change, but climate change itself does not make the problem of dispersion more severe. Okay. Future of eco-friendly cities. Where should I go with this one? This is an open-ended question, but in terms of eco-friendly cities, I would say whatever energy we use, okay, there should be there is an energy budget that we have to keep in mind, okay, which is all the energy that we have coming in is from solar radiation. Okay, even the wind energy that we have, it is because of synoptic winds that are induced by large-scale climatic events. Okay? So in that energy budget, we don't want to trap that energy. Okay, so eco-friendly cities would be where we are taking that energy, but we are also giving whatever is not used is effectively given back. So urban heat islands is something that we should avoid in our future of eco-friendly cities. Green energy is definitely one of them. We should definitely have more vegetation in those cities. So those are some of my thoughts.
Yeah, I thought it was quite interesting how you considered the time frame for climate change and dispersion.
Yeah.
So the next question is, are there current investigations on how to mitigate the smoke that travels during large bushfires?
I'm not aware of any current investigations to do this because, but if I was asked this question to do this, to mitigation of smoke that is traveling due to bushfires, I don't think it is possible. Just because if you want to mitigate or attenuate that smoke or control it, okay, the volume of smoke coming out of large bushfires is so enormous that there is no way to control it. Plus, it's happening over a large scale and you cannot control the wind. Okay? So the only thing that you can control is the source itself, which is what something people try to do. We try to control the spread of the bushfires. We cannot control the smoke that's emerged after that.
Yeah. So I think this will be the last question. What is your academic background and why did you choose to specialize in fluid mechanics?
So my academic background, I did say that in the slides earlier. I am a mechanical engineer as my first training. The reason I chose fluid mechanics is because I wanted to become a pilot, and I wanted to fly a plane. For some reason, I never did that. But anyway, so I wanted to fly a plane, and then which is why I studied mechanical engineering. And then when I went to the US, I did a degree in aerospace engineering. But flying is an expensive hobby, and then you have to find work. So I found work first. And then because of my interest in aerospace, I studied fluid mechanics, which is something which affects flights. So that's how I got into fluid mechanics. The beauty of fluid mechanics is that although we don't have the solution to Navier-Stokes equation, if we understand how to deal with those problems, we can apply the approaches to many different fields.
Yeah. So now I think it's time for a quick photo. If everyone could turn on their cameras, that would be great. I'll just wait a few more minutes to a few more people. All right, okay, I think that would be it. Thank you so much for your presentation, Dr. Kapil Chauhan. It was great. We really learned a lot from that. On behalf of everyone watching, I really appreciate you taking time out of your busy schedule to do this. And with that, the seminar is concluded. Make sure to fill out the final feedback form. And if you have any more questions,
Send me an email.
Yeah, reach out to go through an email.
Thank you, everyone.
Thank you.
Thanks, Sangeeta.